Mark isn't with us today, and it's not for the want of trying. He was really looking forward to coming over to being with us today, but unfortunately, with the flight chaos that's been going on in the past few weeks, he's not been very well for the last couple of weeks either. He's picked up a nasty bug somewhere, but he's thankfully he's made the effort to use this Zoom, and Andy has been brilliant in setting it up. Otherwise, Mark wouldn't have been able to appear today. So it's really nice to be able to introduce him. Now then, I know of at least two people in this room that have been observing OJ287 for 40 years or so. John Toon, probably, and myself. I don't think there's anybody else for 40 years. Oh, right. You're not old enough to be observing for 40 years. But I'm sure that Mark Kidger has been interested in the subject for a lot longer than that. And if you want to know anything about OJ287, then Mark is the man to speak to about. He lives and breathes this subject sometimes. He helps amateur astronomers around the world. He collates a lot of data, and he certainly helped myself over many years in getting data for this target. The title of Mark's talk is a 6.65 day pseudo-periodicity in OJ287's flaring in 2023. So I hope you will welcome Mark from Madrid to Northampton for this talk. Thank you.
This is a classic case of a project where you started trying to do one thing and a completely different result came out. Now, before I start, just an apology. Some months ago, my dentist prevailed on me to start using dental aligners. I'm about halfway through the course, but wearing them, I speak something like Donald Duck, but without his clarity of diction. So I hope people can understand me. It's the shape of my mouth has changed completely over the last 3 months, and it will continue to change. Anyway, subtitle for this is Beware of Periodograms. They're devious, and they are very much a false friend. This is one of the lessons, because variable star observers use periodograms a lot. They like looking for periodicity in things. Do not believe everything you see. So this is, as Gary said, my friend OJ287. I've been observing it for about 40 years. Now, it seemed to be a coincidence. There are a lot of us in the room doing this. And I've spent many happy nights in the telescope observing it and trying to work out what the hell it's doing, because it really has a very perverse sense of humor. And you can see the quasar here. This is a Martin Mobley image, quite an anonymous little thing, typically about magnitude 15. It's at a redshift of 0.306. And if you translate that into light years, that's about 3.5 billion light years, 3,500 million. And it can get up about as bright as magnitude 13, 12 and a half. So if you convert that into absolute magnitude, it comes out at very close to -30 at maximum. That is incredibly brilliant, about 60 trillion suns, or in units that you and I can understand better, about 600 times the Milky Way galaxy. It's a really quite remarkable object. Now, what is even more remarkable is the fact that it varies so violently and so rapidly. This was just a typical night of observation. It was the 24th of January. I picked it more or less at random. There's an observation here from Gary Poyner. I think that was coast in Tenerife. Then a group of points from David Boyd. Often there's data from Steve Arnold as well, but frequently you don't see Steve's data because it's sat right on top of David's, and you cannot distinguish them. And then another observation from Gary, this time with the slow telescope. This change over a few hours is equivalent to switching off 2.5 billion suns. And then between these observations, you've switched back on about 1 billion suns. It's a really remarkable object, the way it varies, what it does. And it's one of the very few variable stars, apart from Algolid eclipsing binaries and a few very short period stars like RR Lyrae, that you can actually see varying at the eyepiece. And Gary has told me he's watched it vary at the eyepiece on many occasions. Here's a typical sample of data from one light night in the spring. And you can see the variations. It was down below 16.5. And then just a week later, it was up above 15. You can see it's varying really from night to night tremendously. Each shape here is a different observer. I've taken off the key simply to avoid cluttering up the plot too much. But you can see it goes up and down very enthusiastically. Now, in 1987, I think it was, a young or relatively young Finnish astronomer called Aimo Sillanpää was doing a PhD. And what he was doing was he was going through the plate collection, glass plates from Tuola Observatory in Finland. And he was estimating the light curves of quasars from them. This is a job, I think Chris Lloyd is in the audience. He will sympathize with Aimo's plight there. And this was the light curve that Aimo built up from the Tuola plate collection for OJ287. That first observation is in December 1891, and he had observations right up to 1987. And he saw this light curve, and he took it to his supervisor at the observatory and said something like, Aimo's got a very characteristic voice, which I can't imitate. It was something like, Maori, I see eclipses. You know, a bit like Churchill, but even deeper. And you can see, really, it's going up and down a lot over the years. And there's something curious going on there. Now, Maori, his supervisor, it's this gentleman on the right. And Maori, he is one of nature's gentlemen. And he's a fantastic guy. He must be about 80 years old now. And he's retired. He's an emeritus for many years now. He looked at the light curve and said, Aimo, I can't see any eclipses in there, but it does look as if you've got regular flares. And he came up with the idea that you might have a giant black hole here with a huge accretion disk. This is the scale. That's 10 light weeks. So if you think the orbit of Pluto is about a quarter of a light day, that gives you an idea of the scale. And then a secondary black hole, not quite so big, going round it. And at the time, they were thinking that the orbit of the secondary black hole was precessing maybe about 5 degrees per orbit. Now, if any of you remembers the case of Mercury, the perihelion of Mercury advances about 10 arc seconds per orbit due to relativistic effects. 5 degrees per orbit, that's something really quite impressive. And because of this work, drew attention to OJ287 And there was a lot of effort to find more observations of OJ287 in different plate collections. And people have been collecting data from places like Sonnenberg in Germany, and they've built up quite a lot of observations. And here's the light curve. I built it up last night, 140 years of data. You can see it's gone down. This was actually an observation of mine. This one here, sorry, no, this one here is an observation of mine. It went down as faint as 17.6. And at brightest, it's been up as bright as magnitude 12. Think how many tens of billions of stars you're switching on and off in that light curve to get these variations. It's really something quite impressive. Now, if you plot it as flux, because radio astronomers, they prefer fluxes, not magnitudes, a linear scale, and infrared astronomy uses fluxes, Janskis and millijanskis. You see something like this, and you can really see that there are a series of big peaks in the light curve. And there is a certain regularity to them. And Imo and Maori, on the much more limited data they said, came up with an approximate period of about 11.6 years. And you can see the arrows which mark the outbursts. They're fairly regularly spaced, which is good. Now, what you can do is you can take the light curve and you can line it up. So you pick a period, and each segment here is one period of the light curve. And you can see that a lot of the big outbursts really do line up. This vertical red line lines up with a few of the outbursts. A number more line up against this second one. It appears the outbursts are double. Typical interval about 13, 14 months between them. However, as I said at the start, and as Gary has learnt to his cost, OJ287 does have a sense of humor. And you get a few outbursts like this one here that don't agree at all. There's another one here, doesn't agree. But you can see the outbursts, they line up more or less. You can believe it. So what do? You do a periodogram, what we would call a Fourier transform analysis. You look at the light curve. What is the dominant period in the light curve? And what you want to see is something around 11.6 years. And most certainly you do not see 11.6 years. In fact, you do see a nice sharp period. The very best period you get is actually 4.12 years, 1,505 days. So what's going on here? And this is the business of periodograms playing you false. Do not believe them, or at least it's more like a phrase. If you've ever seen the film Reach for the Sky about the Second World War fighter, he's Douglas Bader. He says, the rules are for the obedience of fools and for the guidance of wise men. Periodograms are exactly like that. Only a fool believes them, but a wise man lets the periodogram guide them. What is going on here? Well, let's go back to our light curve and have a look at it. Now, at the start here, the first 20 years of data, there are 22 points, if I remember rightly. There's 1 point per year. Over the last few years of data, we've got typically about 4 points per day. And that's including various months in the year where you don't get data because of solar conjunction. So this bit of the light curve totally dominates any analysis you try and do of periodicity in the light curve. And look, there's a flare here, there's one here, there's another one here. They're separated by just about exactly 4 years. So when you see a 4-year period, it's just looking at this most densely sampled part of the light curve and saying, ah. It says nothing about the other 130 years of data. That's the problem with sampling. Unless your data is reasonably well sampled, a light curve like this is absolutely useless to analyze with periodicity analysis. And there was another wonderful example of this. I remember the first conference I ever attended. An Italian group, very distinguished, presented a light curve of another quasar, 3C 345, one that I know Guy Hurst used to observe a lot. And they said, look, there's a splendid periodicity here of 1500 days. And I said, but yes, that periodicity disappeared 10 years ago. And they replied, no, we ran the data again last week and it was still there. And what they had was a similar thing. They had 3 exactly spaced peaks in the light curve early in their data, and they were completely biasing all the analysis. All they were seeing was those 3 regular peaks, even though the periodicity, if you can call it periodicity when you've only got 3 peaks, had disappeared a decade before. So over the years, as we've got more and more data, Maury has been updating the model, improving it. And this is more or less his latest model. So we've got a primary black hole, about 18 billion, that's 18,000 million solar masses. And then a little black hole going around it that's only 100 million solar masses, about a 12-year orbit. And this orbit is very much inclined to the accretion disk of the main black hole. And twice every orbit, it punches through the accretion disk, hits it, causes a big perturbation, and a stream of material flows onto the black hole, floods onto it. But the impact geometry changes every time, or almost every time, every orbit, because of precession, because of perturbations. And so the delay between the time it hits the accretion disk and the material actually reaches the black hole and gives us this enormous outburst can vary from anything from a few months to several years. And Maury also calculates that the advance of perihelion is about 28 degrees every orbit, nothing like 5 degrees. It's absolutely really remarkable. And because of this changing geometry, it turns out that even though most outbursts will be double, there are the 2 impacts, there are a few that are just single. We've just had one of those now. So what's the problem? These outbursts typically last about a month, maybe 2 months. The last one in 2019 occurred exactly at solar conjunction, and the sun virtually occults OJ287 in the summer. How do you observe it? Well, it turned out that the NASA's Spitzer Infrared Observatory was still working. It had been in the Earth-Moon Lagrange point, but it had been allowed to drift away. It had run out of fuel and it was wandering away. It was about 60 degrees around the sun from the Earth by the time of the 2019 outburst. So it could actually see round the edge of the sun. And so Maury made a proposal, got observations made with this telescope. Some of the very last observations that were made with it before it was shut down. And the outburst happened with an accuracy of 2.5 hours compared to the prediction, which is really pretty good considering that there are 18 different variables that he had to fit. Now, a new prediction was made for a lone outburst summer last year, even closer to conjunction. How to observe it? Well, there are no space assets that left at all. There was nothing that we could use to try and observe this outburst. We had a look at one of the solar satellites, the one that's in orbit at the Earth-Sun Lagrange point. It would probably not be able to detect OJ287. So what did Maury do? He gets a lot of people to observe. He gets in touch with me asking if I can get the amateurs to observe and build up as good a database as we can. And he came up with an alternative prediction that possibly, if one particular effect that they'd not taken into consideration originally came into play, the outburst could be delayed until early November. So obviously, we couldn't observe at conjunction. It turned out that the Japanese and the Nordic telescope in La Palma could. They actually got their first data at the end of August, and OJ287 was absolutely normal. And it continued normal. These were some points from Gary. Then Martin Mobley joined in. And then we started watching it going up and up slowly. And we were getting very, very excited. And, you know, if you've seen Gary excited, it's a wonder to behold. And then suddenly down it started to come again. You know, I've been passing our data to Maury, and Maury was getting excited, saying, well, we can predict a really fast rise going to start to happen first week in November if the prediction's right. And it just flopped straight back down. This was a little bit depressing. Wasn't quite what we were expecting. However, we continued observing. A lot of other people continued observing. This is our light curve for the entire year. You can see before conjunction, it's about magnitude 15.3. It's actually a bit fainter after conjunction. And there's this big gap. And by observing very close to the horizon in twilight, other groups, professionals, were able to say, if the outburst happened, it was exactly at the time of prediction. It had occurred right here in the center of the gap, unseen. We can't disprove it. We cannot prove that it didn't occur, but we can only say that if it happened right in the middle of that gap. So it's a sort of negative confirmation. So here's the plot of the BAA and the Spanish data over the winter. What I've done is here I've shown the key, all the different observers, the different telescopes you used. And you notice something. September, October, you see a slow variation. November to the end of December. And then early in January, about mid-January, suddenly something changes. And we started seeing a series of very rapid outbursts, which was curious because this is not normal behavior in OJ287. And I kept getting emails from Gary saying, it's going up again. And then 2 or 3 days later, false alarm, back down again. And I was entering the data for these observations usually just about every day. At this point here, late January, this was my last month at work. I was working for 4 different missions, extremely stressed, trying to get finished jobs that I had to get done before my last day at work. But I was trying to keep up with the data, and I was beginning to see a trend. If it hadn't been for so many excited emails from Gary, it's getting brighter, maybe I wouldn't have noticed it. So here's mid-January to late March on an expanded scale. And you can see it's brighter, goes down again, brighter, goes down again, brighter, goes down again, brighter. And it seemed that these peaks were happening about every 7 days. And now, normally, when you see flares in OJ287, the little flares, they're about half a magnitude amplitude. They last 10 days, 2 weeks, and you maybe get one every month, month and a half. This was very different. I was extremely curious. So, consulting, I was told download Peranso. And so I got in contact with the guys at Brussels, downloaded it. And no, I hadn't done any periodogram analysis for a few years. Having Peranso, it was like an American would say, a kid in a candy shop. It is fantastic, the things it does. And so I started to analyze the data, and lo and behold, there was a nice sharp peak in the analysis at around 7 days. This peak here is just the lunar month, because the moon passes almost on top of OJ287 once a month. But this peak really was curious. And I started looking at the data and trying to line up the different maxima using this period. And it didn't work. And something else was happening, was really annoying me. Every time I added more data, the period that I was finding in the light curve changed. And this was getting really annoying. And as Gary will testify, got a bit frustrated with this. And then suddenly I had one of these eureka moments. Unlike Archimedes, I did not get out of the shower and run around the garden naked. I just went to the computer instead. Conserve decency. And I realized if I split the data into 2 halves, took one set of data from January to mid-March, I got an even better period. There's your monthly lunar cycle, and you get a really sharp period, 6.65 days, and the errors on that is about plus or minus 0.02. Tremendously strong period. Then I did another analysis, the data from late March to the end of May. This was my period analysis. There is nothing. So, flashback. Sharp period. Second half of the data set, there is nothing at all. That's why the results I was getting with my periodogram analysis were changing. Because the more data I added, the more garbage I was adding to my analysis. So when I realized and got rid of the garbage, suddenly the result became absolutely clear. And you can do all kinds of wonderful things with Peranso. And so I folded the light curve over 6.65 days. Whoops. And you can see it's reasonably convincing. You've got a fairly fast rise, a slower decline, and you can see that even though the amplitudes change, they all follow more or less the same pattern, which was great. And then this was the final test. If I took one well-observed period, which was this one, and then added 6.65 days time and time again and subtracted it, did the periods, the peaks line up? And yeah, more or less they do. There are some, this one doesn't happen. There are a few that are a bit offset. There's one here that's an interloper, but most of them, there's a peak just about the time you'd expect. It's not a stable period. It's what an astronomer calls a quasi-periodic oscillation. It's fairly periodic, but not perfectly periodic. But there's definitely something there in the signal. So what do I think is happening there? Well, from the giant black hole, we've got a relativistic jet. So you've got the accretion disk, which is eating up material, and the excess, the indigestion, what the black hole cannot eat, goes out of the pole of the black hole as a relativistic jet. So the material is accelerated to 0.2, 0.3 times the speed of light. And it turns out that in OJ287, OJ287 is very special because we see it just about pole on. In fact, of all the quasars, it's the one where we see deepest into the throat of the jet. It's not the best aligned. There's one even better aligned, but it's a redshift 10 times as great. So we don't see as far inside the jet coming out of the black hole. What is happening in this jet? Well, the material isn't being shot out at an even rate. There are lots of shocks in it. Sometimes there's more, sometimes there's less. There are huge shock waves in the jet, this material coming out towards us. And because it's relativistic, it's beamed. So if you're looking down the jet, it's like looking down a lighthouse beam. Much more brilliant. The light is concentrated in our direction. And so what is happening is when one of these shocks goes across our line of sight, we see a flash of light. And what is effectively happening is something like this. You've got a strong magnetic field in this jet, and you've got lots of electrons floating around, and they're spiraling around the magnetic field lines violently. And as they do so, they emit synchrotron radiation, send out photons. Those point in our direction down to the telescope and the observer, and we detect a flash of light. So basically what is happening is every time this spiraling beam crosses our line of sight, we see a flash. When it stops crossing our line of sight, we stop seeing the flashes. So to finish up, what happened? Well, it looks as if just for a few weeks early in the year, we got this beam of light from a shock in the jet coming out of OJ287, lining right up with us. And every time it lined up almost perfectly, we saw a flare in the light curve. Now, because we can see more flares than just these periodic ones, we know there must be more shocks. There must have been a whole lot active, but only one of them was spiraling across our line of sight in a regular fashion. And then after a couple of months, either it just decayed, it moved out of our line of sight, stopped beaming for some reason, and these flashes disappeared. So anyway, that very briefly is the investigation that came out of this light curve. There's a paper soon to come out in the BAA journal. I'm trying to get it on archive, but as I am no longer an accredited researcher, I have to find somebody who is at ESA who can vouch for me and give me permission to put it on. I'm still working on that one. Somebody tried and was not sufficiently authoritative to accredit me. But anyway, it will be on archive, I hope, in the next few days, this paper, now that it's accepted. And thanks very much indeed. If that's Gary talking, I can't hear
Thank
you.
you, Mark. Can you hear me now, Mark?
Yep, I hear you much better.
Right. Thank you very much for that. That was brilliant. I'm sure there must be some questions in the audience. Yes, right, hang on. Will this microphone work?
One on, if you.
Okay, so Chris, do you want to give you a question in for that, please?
Thanks, Gary. Mark, I used to associate it with a black hole that size being one in the center of a galaxy. Are you saying that this star is by itself with a companion black hole, but is not associated with any galaxy? Isn't that strange?
I didn't hear that question. I didn't hear the question very clearly.
Okay, Mark, can you hear me now?
Yes.
OJ287, can you say something to us about its associated galaxy, please?
Right. Okay. So we can't see the galaxy. That's one of the curiosities with this little beast. That the quasar in the center is so brilliant, it's much more brilliant than the galaxy. Now, the only thing you can say is that when it's very faint, around about magnitude 16.5, the colors of the quasar start to change and they get redder and redder, tending towards the colors of a giant elliptical galaxy. And there are some observations in the infrared. The infrared picks up the giant evolved stars in giant elliptical galaxies, which seem to show a little bit of galaxy pointing out from or behind the quasar. And it does look like it's a giant elliptical galaxy, probably pretty brilliant, maybe 100 times as brilliant as our Milky Way. But it is completely and utterly overwhelmed by the light from the quasar. So at the moment, all we've got is best guesses, but it does look like it's a giant elliptical. Something like the James Webb would be good for this.
Mark, can you hear me?
Yep, I hear you perfectly.
Okay, David Boyd here. Question
Hi,
is,
David. Love your
hello.
date in that light curve.
Thank you. If your explanation is correct, can it make any predictions which can be tested in the future?
Certainly there is one prediction that I haven't tested, and that is that the amplitude of those flares, if they're synchrotron flares, should be bigger in blue than in red. So I haven't done this test yet. It only occurred to me yesterday. But I've got quite a lot of data in red filter, a lot more in V, and I've got possibly enough data in a blue filter that I can work out whether or not this prediction is right. That there is actually, it's much bluer than the normal radiation from the quasar. And that's something I'm going to look at over the next few weeks when I get time. So that's one prediction. A second prediction I make is that when they see this paper on archive, some polls who've been coordinating data for Maori, and they're very sniffy about amateur data, I'm afraid to say, are going to be a little bit miffed, because one of them made a chance remark to me in October that he said he thought he could see the light curve oscillating with a period of about 6 days or a week. And I've seen nothing more about that. And I know they were looking for this kind of oscillation. And I am very much hoping that we've beaten them to it.
I have to say, Mark, because I think sometimes, can you hear me?
Yeah, I hear you.
Sometimes amateurs can get a little bit sniffy with their professional data too, but that's another story.
Yeah. Yeah, I am well aware of that, having a foot in each camp. It's an interesting position. It's like the peacekeeping force between two angry tribes. Both sides shoot at you, but still,
Right,
it's
we've
a
got
lot
another
of fun
question.
when things work.
We've got another question.
Hello, Mark. I was wondering, on the orbit of the two
Who's
black
speaking?
holes,
Sorry, who's speaking? Just let me
Can you say
know.
your name, please?
Martin Ellsmore,
Okay, Martin, thank you.
do the black holes ever get close enough to be detected by the upgraded LIGO?
Right. This is a very good. LIGO cannot do it. The masses are far too large to be detected by LIGO. But they could, in theory, I believe, be detected by the LISA satellite that ESA wants to put into space in 2034 was the last estimate. LISA should, in theory, be able to do it. Now, the other thing is the Whole Earth Telescope. This amazing combination of radio telescopes all around the world. They wouldn't detect gravitational waves like LISA, but they can do radio maps that should be able to detect if there is a binary black hole. And I know that Maori has been in the ear of these people. If you remember a couple of years ago, there was the announcement, the first images of a black hole in the center of a galaxy, which was M87. And I believe that they've been taking observations, and I'm hearing rumors that they have found something. So we may actually get something on two fronts: gravitational waves from LISA, and one of Maori's more extraordinary predictions is that the secondary black hole is spiraling into the primary, and in about 50,000 years, they will collide. And if we don't get it from the LISA satellite, it is just possible that the Whole Earth Telescope may actually be able to see these two black holes and resolve them. So one of two.
Thanks, Mark. Time for one more question. Anybody's got one? No? Okay, well, thanks again, Mark, for a wonderful talk. And everybody in the room really appreciates you getting out of your sick bed and spending the Saturday afternoon with us. It's great that
Yeah.
we could actually get your talk here today. Just a shame you couldn't
Yeah.
make it.
I'm enjoying the talks that I'm listening to. The previous talk, I remember using Optech in the observatory in Teide, and we did observations with it. Much easier to use than a CCD. If you want to observe bright variables, bright eclipsing binaries, don't use a CCD. Use Ian's photoelectric photometer. It is so simple.
I think Chris Lloyd's been saying that for years, to be fair. Anyway, thanks, Mark. It's been brilliant. And could we just show a report?